Hello everyone, my name is Nana and I'm from the Pudhi Academy. So today we'll continue with the chapter that is chemical bonding and molecular structure. So today we'll basically deal with hybridization, features of hybridization, types of hybridization. So there are three main types of hybridization: sp, sp2 and sp3. Other than these three hybridization, we'll be also learning about the hybridization involving d orbitals, and they are sp3d and sp3d2. So let's start. First, let's start with hybridization. Now, in our previous class, we have seen about the VSEPR theory and valence bond theory. Then we have also seen about one more theory, that is molecular orbital theory. Now, before doing the molecular orbital theory, it is important for you all to understand what is hybridization. Now, hybridization, it is a characteristic in order to explain the characteristic geometrical shapes of polyatomic molecules. Pauling is the one who introduced the concept of hybridization. Hybridization, it is basically introduced to explain the geometrical shapes of polyatomic molecules. According to him, the atomic orbitals combine to form new sets of equivalent orbitals known as hybrid orbitals. So atomic orbitals, when they combine together to form a new set of equivalent orbitals, they are known as hybrid orbitals. Now, unlike pure orbitals, the hybrid orbitals are used in bond formation. So normally atomic orbitals, they consist of electrons. Now the electrons present in those orbitals are the ones which are involved in bond formations. So once these orbitals are hybridized, the hybrid orbitals are the ones which are used in the formation of bonds. Now this phenomena is known as hybridization, now, which can be defined as the process of intermixing of the orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new sets of orbitals of equivalent energies and shapes. So hybridization, which can be defined, it is a process of intermixing of the orbitals slightly different in energies. So we intermix orbitals which are slightly different in their energies and we redistribute their energies. So the energies are redistributed so that they attain similar energy as to stabilize themselves and form an equivalent energy and a shape. Now, for example, when 1 2s and 3 2p orbitals of carbon hybridize, there is the formation of 4 new sp3 hybrid orbitals. So about sp3 hybridization we will discuss later in detail, but you have to remember, from a carbon, when there is hybridization of 2s orbitals, one of the 2s orbitals, and there are 3 2p orbitals. So when they are hybridized, we get 4 new orbitals, and that orbitals is called as sp3 hybrid orbitals because we have hybridized 1s orbitals and 3 p orbitals. Now how they are hybridized and all, we will be learning further. What are the salient features of hybridization? What are the important features of hybridization? Now, the main features of hybridizations are: the number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. So main point is, if there is 2 atomic orbitals which are hybridized, that means there are 2 molecular or 2 hybrid orbitals that are formed. So the number of atomic orbitals that get hybridized is the number of hybrid orbitals that we get. The second point, the hybridized orbitals are always equivalent in energy and shape. So whichever hybrid orbitals are there, all the hybrid orbitals will have an equal energy. There won't be any high or low energy. The energy will be equal and they will always have a shape. Next point is, the hybrid orbitals are more effective in forming stable bonds than pure atomic orbitals. So hybrid orbitals, they form a stable bond rather than an unstable bond. okay, formed by pure atomic orbitals. Now the pure atomic orbitals, the bond which is formed using them are like more. If there is an electronegative element, then the bond will be more towards electronegative element, or the strength of the bond is more towards them, so it is easy to break the bond. So when there is a pure atomic orbital is involved in bond formation, it is rather unstable. So hybrid orbitals are considered to be forming a more stable bonds. Next, these hybrid orbitals are directed in space in some preferred direction to have minimum repulsion between electron pairs, and thus a stable arrangement is attained. So hybrid orbitals, they direct themselves in space in such a way that there is minimum repulsion between the electrons. So when there is minimum repulsion, there won't be any instability, okay, because everything will be arranged in such a way that there is minimum repulsion and the molecule attains a stable arrangement. So therefore the type of hybridization indicates geometry of the molecule. So hybridization, it also indicates the geometry of the molecule, because to attain a stable compound, they will arrange themselves in such a way that there is a minimum repulsion. So that arrangement will give you the geometry of the molecule. Important conditions of hybridization. The orbitals present in the valence shell of the atom are hybridized. So here, what is the main point? That valence shell, okay, the orbitals which are present in the valence shell of the atom are hybridized. Not entire orbital is hybridized, only the valence shell orbitals are hybridized. Then the orbitals undergoing hybridization should have almost equal energy. So this point we have already seen. After hybridization, the orbitals or hybrid orbitals have an equal energy. So the orbitals which undergo hybridization, they should also have almost equal energy. Promotion of electron is not essential condition prior to hybridization. Promotion of electron means excitation of electron. There is no need for electrons to get excited for the process of hybridization. But eventually there will be excitation of electrons, but it is not necessary that it should occur before hybridization. It can occur after hybridization also, or during hybridization also. It is not necessary that only half-filled orbitals participate in hybridization. In some cases, even filled orbitals of valence shell take part in hybridization. Now, every time when hybridization takes place, you can see there is some unpaired electrons. We call them half-filled orbitals, but it is not always necessary that the orbital should be half-filled for the hybridization to take place. Even some completely filled orbitals of valence shell also take part in hybridization. With this, we will move to the types of hybridization. Now, there are various types of hybridization, and they involve s, p and d orbitals. Now, first we will see hybridization involving only s and p orbitals. After that, we will involve the d orbitals into them. First, let's start with sp hybridization. Now, this type of hybridization involves the mixing of one s and one p orbitals. So when we mix one s and one p orbitals, now this can be of any energy level. It can be 2s, 3s, okay, any energy level, but only one s orbital and one p orbital is involved in the process of sp hybridization, giving you an sp hybrid orbital. Now, the suitable orbitals for sp hybridization are s and pz. So as you know, p orbital have three sections: px, py and pz. So when there is sp hybridization, it is always convenient to hybridize the pz orbital, that is the last orbital of the p block. Okay, now if the hybrid orbital are to lie along the z-axis, now each sp hybrid orbitals have 50% s character and 50% p character, because you have one s and one p orbital, so their characteristic will be also equally divided. So the orbit or the hybridized orbital will have a characteristic having half of s orbitals and half of p orbitals. Such molecule in which the central atom is sp hybridized are linked directly to other central atoms possessing linear geometry. So in sp hybridization there is a linear geometry which is observed. This type of hybridization is also known as diagonal hybridization. Okay, so sp hybridization, it shows a linear geometry, and this type of hybridization, it is also known as diagonal hybridization. The two sp hybrid points in the opposite direction along the z-axis with projecting positive lobes and very small negative lobes. You know, right? P block or p orbitals, they are depicted in a lobe form. One lobe with positive end and another lobe with negative end. Now, when we draw an sp hybrid orbitals, okay, or when we show them along the axis, in that case positive lobe and negative lobes are shown in such a way that positive lobe is bigger and negative lobe is smaller. Okay, and which provides more effective overlapping, resulting in the formation of stronger bond. Now this bigger and smaller size depiction, it allows the orbital for more effective overlapping. So the overlapping is done to the maximum if the orbitals are in this format, which results in the stronger bond formation. So during the overlapping concept, I have explained you that more the overlapping, stronger is the bond which is formed. So same thing happens here. Now an example for sp hybridization is BeCl2, that is beryllium dichloride. Now here beryllium is the central atom, so obviously the one which will be undergoing hybridization, or the orbitals which will undergo hybridization, is your beryllium. Okay, now beryllium, if we write its electronic configuration, it will be 1s2 2s2, because the atomic number of beryllium is 4. Okay, so it will be 1s2 and 2s2. Now this will be its electronic configuration in ground state. But when beryllium enters an excited state, what will happen? We have to shift one of the electron from the s orbital to a vacant p orbital. Okay, now in this case, in the excited state, one of the 2s electron is promoted to the vacant 2p orbital to account for its bivalency. Why we want bivalency? Because the hybridization is sp hybridization, right? So ground state, we have 1s and 2s, two electrons each. Okay, for beryllium, when it goes to excited state, 1s will remain like that only, it won't get affected, but the electron in 2s orbital, okay, the electron in 2s orbital will be shifted to 2p orbital, to a vacant 2p orbital. So it will be like this. So here now you can see 2s and 2p, one unpaired electron in s orbital and one unpaired electron in p orbital. So this will give rise to sp hybrid orbitals, and these are the hybrid orbitals. Okay, one s and one p orbital gets hybridized to form sp hybridized orbital. This is called as hybridization. Okay, now these two sp hybrid orbitals are oriented in opposite direction, forming an angle of 180 degree. So these both the orbitals, these are hybrid orbitals, right? Both the hybrid orbitals are arranged in such a way that they form a linear structure. Okay, they are arranged to opposite to each other. Okay, in that form they form a linear 180 degree structure. Now each of the sp hybrid orbitals overlap with the 2p orbitals of chlorine axially and form two beryllium chlorine sigma bonds. Now in this case what will happen? Now we have to satisfy this electrons. Since they are singly paired, we have to add some molecules to balance them out. So to balance them out, what is done is we take two chlorine molecules, and each chlorine molecule donates one electron to this empty shell or these singly paired electrons. Okay, now you have both s orbital and p orbital filled, so that will give you a linear chlorine beryllium structure. Okay, so this is how sp hybridization is. Next one is your sp2 hybridization. Okay, now in sp2 hybridization, in this hybridization there is involvement of again one s and two p orbitals, because it is sp2, so there is involvement of two p orbitals. For example, in boron trichloride, so here boron becomes your central atom and you have three chlorine molecules to complete the hybridization process. So again, now the ground state electronic configuration of boron is 1s2, 2s2 and 2p1. Yes or no? Because boron, the atomic number is 5. So this is what the ground state electronic configuration of boron is. Now when it goes to excited state, what will happen? 1s2 will remain like that only, but 2s and 2p will change. One electron from 2s will be transferred to 2p, making it 2s1 and 2p2. So if I draw an orbital structure, it will be, there will be one electron in 2s orbital and two electrons in 2p orbitals. So this gives rise to sp2 hybridization. One s orbital and two p orbitals are involved. Okay, the same thing with the structure. In excited state, one of the 2s electron is promoted to vacant 2p orbitals. Now as a result, boron has 3 unpaired electrons. Yes or no? 3 unpaired electrons, 1 in 2s and 2 in 2p orbitals. So total 3 unpaired electrons. Now these 3 orbitals hybridize to form 3 sp2 hybrid orbitals. Now how 3? 1, 2 and 3. So 3 sp2 hybrid orbitals. Now the 3 hybrid orbitals so formed are oriented in a trigonal planar arrangement. So sp2 hybrid orbitals, in what way they are arranged geometrically? They are arranged in a trigonal planar arrangement and overlap with 2p orbitals of chlorine. Now these 3 unpaired electrons are satisfied with 3 electrons from chlorine. So they are arranged trigonally so that the p orbitals from chlorine can combine with them to satisfy each other. So these 3 unpaired electrons are paired up by each electrons donated by chlorine, thus forming the BCl bonds, 3 BCl bonds. Now the geometry is trigonal planar and the angle, bond angle will be 120 degree. Next is a sp3 hybridization. Now this type of hybridization can be explained by taking the example of CH4 molecule, in which there is mixing of 1s orbital and 3p orbitals. So similarly, how we have done s and p orbitals, you have sp and sp2 hybridization. Now we have sp3 hybridization. Here with those two examples you can clearly state that you will have 1s orbital and 3 p orbitals. Now the example here taken is CH4, that is methane. So here carbon will become your central metal atom or central atom. Now Carbon in ground state, its electronic configuration will be 1s2, 2s2, 2p, 2, right? Because carbon is 6. Carbon atomic number is 6. So it will be 1s2, 2s2 and 2p2. Now, in excited state, what will happen? Again, 1s will remain like that only. From 2s, 1 electron will be shifted to 2p. So it will become 1 s orbital and 3 p orbital are unhybridized or are hybridized to form sp hybrid orbital. So total how many will be there? There will be 4 sp3 hybrid orbitals. How 4? 1, 2, 3 and 4. 1s and 3p. So total you have 4 sp3 hybrid orbitals. Now here in sp3 hybridization you have 25% of characters given by s orbitals and 75% characters are given by p orbitals, because there are 3 p orbitals and only 1 s orbitals. So 75% of the character of that hybrid orbital will be from p orbitals, and it forms a tetrahedron structure. Now the angle will be also 109.5 degree. So the structure in this format is your NH3 and H2, ammonia and water. Okay, can be explained using sp3 hybridization. In ammonia, the valence shell or outer electronic configuration of nitrogen in ground state is 2s2 and 2p3, having 3 unpaired electrons in sp3 hybrid orbitals, and a lone pair of electrons is present in the fourth one. Okay, so there is a lone pair of electrons. So this 2s2, it is the lone pair of electrons. Now these 3 hybrid orbitals overlap with 1s orbitals of hydrogen atom to form the NH sigma bond. So here you can have, this is the lone pair, which is the third hybrid orbital or the s orbital. Okay, s2 you had no, so that is converted into the lone pair, and the other 3 are hybridized and are paired up with hydrogen molecule. Now these 3 hybrid orbitals, they overlap with 1s of hydrogen and forming NH sigma bonds. Now we know that the force of repulsion between the lone pair and a bond pair is more than the force of repulsion between 2 bonded pair electrons. So the molecule thus gets distorted and the bond angle is reduced to 107 from 109.5 degree. So eventually, when we started with the discussion, I told you that sp3 hybridization has an bond angle of 109.5 degree, but the bond angle of ammonia or NH3 is 107. This is because there is repulsion between lone pair and bond pair. Okay, the repulsion between lone pair and bond pair is more than the repulsion between bond pair. So what will happen is the lone pairs will push the bond pairs in such a way that the repulsion is minimized. In that form, the structure is distorted, which reduces the bond angle. So you can get a question why the bond angle of ammonia is 107 even though it follows the sp3 hybridization, and the reason is simple. It is because of the lone pair bond pair repulsion, which is more than the bond pair, and because of the repulsion the shape is distorted, hence leading to the reduction of angle. Okay, so the geometry of such molecule will be pyramidal. From tetrahedron it will become a pyramidal structure. Now, in case of H2O, the molecule in H2O molecule, the 4 oxygen orbitals 1 s 2 s2 and 3 2p undergo sp3 hybridization, forming 4 sp3 hybrid orbitals. Since it follows sp3 hybridization, there will always be an 1 2s orbital and 3 2p orbitals involved. Now, out of which 2 contains 1 electron each and the other 2 contains pairs of electron. So here what will happen is, in ammonia what happened, you had 1 lone pair and 3 bonded pairs, no? But in case of water molecule, oxygen has 2 lone pairs and 2 bond pairs. Okay, you have 2 lone pairs and 2 bond pairs. Now these 4 sp3 hybrid orbitals acquire a tetrahedral geometry with 2 corners occupied by hydrogen atoms while the other 2 by lone pairs. So they form a tetrahedral structure where 2 corners are occupied by hydrogen molecules and the other 2 corners are occupied by lone pairs. The bond angle is again decreased to 104.5 degree. Okay, this is again same reason, there is repulsion between lone pair which is more than the bond pair lone pair and bond pair repulsion, hence giving rise to the decrease in bond angle. Now other than this, sp3 sp2 and sp hybridization have examples involving alkenes, alkanes and alkynes. For example, sp3 hybridization is involved. A basic example that can be given is C2H6. Okay, now C2H6 is a ethane. So sp3 hybridization, an example is ethane. Now in ethane molecule, both the carbon atoms assume sp3 hybrid state. Now we have 2 carbons, right? Both the carbons are said to have an sp3 hybrid state. Now one of the 4 sp3 hybrid orbitals of carbon atom overlaps actually with similar orbitals of other atom to form sp3 sigma bond. So when both the carbons are said to be sp3 hybrid, the sp3, one of the, now there are 4 orbitals which are hybridized, right? 1s and 3 p orbitals. Amongst them, one of the orbital, okay, one of the hybrid orbital overlaps with the carbon molecule. For example, like if I take the s orbital of one carbon which is hybridized, gets overlap with the s orbital of the second carbon which is hybridized, thus forming an sp3 sigma bond between the carbon molecule. And remaining 3 are used in the formation of carbon hydrogen bonding. So there are total 6 carbon hydrogen bonding which are involved. So one orbital of both the carbons are involved in sp3 sigma bond formation between the carbon molecules, and the other molecules are involved in, other 3 hybrid orbitals are involved in the formation of CH bonds. Now, therefore, in ethane, CC bond length is 154 picometers and CH bond is 109 picometers. So, because of their sp3 sigma bonds, the bond length of carbon is greater than the bond length of carbon hydrogen, because carbon hydrogen bond length is, the bond is formed between sp3 hybrid orbital of carbon and s orbital of the hydrogen. Now, second example for sp2 hybridization is ethene. For sp2 hybridization, they form double bonded molecules, that is ethene. In the formation of ethene molecule, one of the sp2 hybrid orbital of carbon atom overlaps axially with sp2 hybridized orbital of another carbon atom to form a Cc sigma bond. Similarly, how carbon-carbon bond was formed in ethane, again in ethene also there is sp2 bond which is formed between carbon and carbon, while the other two sp2 hybrid orbitals are each involved or are each used for the formation of sp2s sigma bond with the hydrogen atom. Now, the unhybridized orbital of 2px or 2py, one of the carbon atom overlaps sidewise with the similar orbital of the other carbon atom to form a weak pi bond. Now, this I will explain you. Now, carbon atomic number is 6. There are 2 carbon atoms. So, when you have an hybridized orbital, initially carbon will have so 2 electrons in 2s orbitals and 2 electrons in 2p orbitals. Yes or no? Now, these both the 2s orbitals, they will overlap to form an sp2 hybrid orbitals. Now, the other remaining 2 electrons of each will be involved in the formation of here what will happen, this carbon from 2s an electron will be shifted to 2p. Okay. I'll explain it here. Now, for sp2 hybridization of ethene, what will happen is carbon 1 and carbon 2. In ground state, both the carbons will have electrons arranged in this format, 2 electrons in 2s orbitals and 2 electrons in 2p orbitals. Okay. One of these electrons are shifted to the p orbitals in excited state. So, this is what happens in excited state. Since ethene follows sp2 hybridization, only these orbitals are involved in bond formation. In this case, what happens, carbon-carbon, there is a sigma bond is formed, and this sigma bond is formed between sp2 hybrid orbitals. Now, these hybrid orbitals can either be any one of them combining with the other one. For example, if I take s orbital, 2s orbital of carbon 1 and 2s orbital of carbon 2, they both combine together to form this sigma bond. Okay. Now, the remaining 2p orbitals remaining 2 orbitals in 2p, okay, they are involved in the hydrogen bonding, okay, CH bonding. Now, ethene, you know, it forms a double bond. Now, that double bond is formed by combination of the unhybridized orbitals. Okay, both of them have one unhybridized orbitals. Now, both of these unhybridized orbitals are involved in the formation of the double bond, which forms a pi bond. Okay, so this pi bond is formed from the unhybridized 2p orbitals. Therefore, it is comparatively weak. Okay, it forms a weak pi bond which consists of two equal electron clouds distributed above and below the plane of the carbon and hydrogen. Okay, so that double bond, one is a sigma bond which is formed from the hybridized orbital, and the pi bond which is formed from the unhybridized orbital. Now, thus in ethene molecule, the carbon-carbon bond exists in one sp2 sigma bond and one pi bond between p orbitals which are not used in the hybridization and are perpendicular to the plane of molecule. So as I showed you earlier, so there are two bonds, double bond which is formed. So there is a sigma bond and a pi bond which is formed. So sigma bond is basically the sp2 hybridized orbitals which are involved, and which is stronger, and pi bond is formed between the unhybridized molecule which is weaker in nature. Now, last one is a sp hybridization, and sp hybridization is involved in ethyne molecule or the molecule with triple bond. So in the formation of an ethyne molecule, both the carbon atom undergo sp hybridization having two unhybridized orbitals, 2py and 2px. So since I showed you how double bond is formed, you can imagine how triple bond is formed. One will be a sigma bond with sp-sp hybridized carbon and the two hydrogens. Similar to sp2 hybridization, sp hybridization is also same. Here what will happen, carbon 1, carbon 2. I'll straight away show you the excited state. Okay, so in excited state, we will have one electron in 2s orbital, 3 electrons in 2p orbital. Okay, now here what will happen, only two of these orbitals will be involved in the hybridization. Okay, from s orbital, one s orbital and one p orbital will be involved. So the remaining two unhybridized orbitals, okay, these remaining two unhybridized orbitals are involved in the formation of triple bond. Okay, similar to how double bond was formed, now triple bond is formed with the two unhybridized orbitals. So this is a sp hybridization of ethyne is. Hybridization of elements involving d orbitals. Now we have seen sp hybridization and some of the examples. Now let involve a d orbital into them. Now the elements present in the third period contain d orbitals in addition to s and p orbitals. Okay, along with s and p orbitals there is an addition of d orbital. Now the energy of 3d orbitals are comparable to the energy of 3s and 3p orbitals. Now 3d orbital, you know, d orbital, it starts from the third series, right? So it has a 3d third energy level. So the energy level of 3d molecule or 3d orbital is comparably same to 3s and 3p orbitals. Now the energy of 3d orbitals are also comparable to those of 4s and 4p orbitals. It is not only comparable to 3s and 3p, it is also comparable to 4s and 4p. As a consequences, we have hybridization involving either 3s, 3p and 3d or 3d, 4s and 4p. In simple words, you can have sp-d hybridization or dsp hybridization. Now in sp-d hybridization, it is 3s, 3p and 3d orbitals which are involved. In dsp hybridization, it is 3d, 4s and 4p orbitals which are involved. Okay. Now the important hybridization schemes involving sp and d orbitals are summarized in this table. So the shape of sp or dsp2, okay, dsp2 means 3d 1 orbital, 4s 1 orbital and 4p 2 orbitals. which are hybridized. It forms a square planar structure. Then again we have a trigonal pyramidal structure with sp3d hybridization, a square pyramidal structure with sp3d2 hybridization, and we get octahedral structure for both sp3d2 or d2sp3. So here we will be doing sp3d and sp3d2 hybridization. Now formation of PCl5 follows an sp3d hybridization. So the ground state and excited state of phosphorus is shown here. Since PCl5, phosphorus becomes the central element, so the hybridized orbitals will be from phosphorus. So in ground state, phosphorus has completely filled 3s orbital and half filled 3p orbital. Now from this s orbital, one of the electron is shifted to 3d orbitals, okay, giving rise to sp3d hybridization. Now how many unpaired electrons are there? 1, 2, 3, 4 and 5 unpaired electrons are there. So these 5 unpaired electrons are balanced by addition of 5 chlorine molecules. That's why it is PCl5. Okay. Now we have 5 hybridized orbitals. Now the 5 orbitals, 1s, 3p and 1d orbital. Total 5 orbitals are available for hybridization to yield a set of 5 sp3 hybrid orbitals, which are directed towards the 5 corners of the trigonal pyramidal. So this geometry is trigonal pyramidal. So this is the geometry of PCl5. Now it should be noted that all the bond angles in trigonal bipyramidal geometry are not equivalent. Okay, all the bond angles are not same. There is change in their bond angles. Now in PCl5, the 5 sp3d orbitals of phosphorus overlap with the singly occupied p orbitals of chlorine atoms to form 5 PCl sigma bonds. Now there is a formation of 5 PCl bonds. Here 1 electron from phosphorus, 1 electron from chlorine. So altogether we form 5 PCl bonds. Now all these 5 PCl bonds are formed in a sigma format. They are sigma bonds. Now amongst them 3 PCl bonds, they lie in same plane or one plane. Okay, hence their angle is 120 degree with each other. Now these bonds are termed as equatorial bonds. The remaining 2 PCl bonds, one lying above and other lying below. Since it is a trigonal bipyramidal, the trigonal shape which is formed, they have an angle of 120 degree and they are in one plane. The ones which are on top and below, okay, the remaining PCl bonds, 2 PCl bonds, one on the above, one on the one below, which forms an equatorial plane, they form an angle of 90 degree, okay, with the plane. Now these bonds are called axial bonds. Okay, these bonds are called axial bonds since they are present in one axis. Now as the axial bond pairs suffer more repulsive interaction from the equatorial bond pairs, therefore axial bonds have been found to be slightly longer and hence slightly weaker than the equatorial bonds, which makes PCl5 molecule more reactive. Now why PCl5 molecule is more reactive? It is said that the equatorial bonds, okay, equatorial bonds means both these bonds, okay, both these equatorial bonds are said to be facing more repulsion than the axial bonds, okay. Sorry, the axial bond pairs, these are axial bond pairs. The axial bond pairs, they face more repulsion than the equatorial bond pairs. Hence, it is found that the axial bonds are far away from the or they are little far from the phosphorus molecule, hence forming a weak bond. Since they are weaker in nature, it is easy to break that bond and replace that chlorine molecule with something else. Because of that, PCl5 molecule is considered to be more reactive. Now, second one is a SF6, okay, which forms an sp3d2 hybridization. Now in SF6, central molecule is your sulfur, or central atom is your sulfur, which has a ground state electronic configuration where you have completely filled s orbital and a partially filled p orbital, that is 3s2 and 3p4. Okay, in excited state, the available 6 orbitals, that is 1s, 3p and 2 d orbitals. Now which are the 2 d orbitals? 1 electron from the s orbital, 1 electron from the p orbital is shifted to the d orbitals, forming 6 hybrid orbitals. Okay, 1 s orbital, 3p and 2 d orbitals, hence it is sp3d2 hybridization. Now they are balanced by addition of 6 fluorine molecules. Now these orbitals, hybrid orbitals, to form 6 new sp3d2 hybrid orbitals, which are projected towards the 6 corners of a regular octahedron. Since there is 6 hybrid orbitals, they form an octahedral structure. Now 6 sp3d2 hybrid orbitals overlap with singly occupied orbitals of fluorine atom to form 6 SF sigma bonds. So there is 6 SF sigma bonds which are formed, because to satisfy these 6 unpaired electrons, each fluorine donates 1 electron from its orbit, which forms 6 sigma SF bonds, and it forms a octahedral structure. Thus SF6 molecule has a regular octahedral geometry. Okay, so in today's video we have seen about the hybridization, what is hybridization, types of hybridization, features of hybridization. So in our next video we will learn about the molecular orbital theory. So thank you for watching my video. Please do like, share and subscribe to our channel.